Gordon Spleet and everyone to this week's IndustryCast, sponsored by CapEx Sales. We are excited this week. We've got Gordon Spleet on with us. We're going to talk about custom machinery, custom leak test equipment. We're going to talk about gauge R&Rs for custom leak test equipment. We're going to talk about what you need to provide to your custom machine builder so that they can properly quote the product, estimate the cycle time, and work through some of those specifics. We're going to talk about differential versus absolute leak testing and how that affects the gauge R&R. We're going to give some examples, show some examples. We're going to talk a little bit about sealing, so simple sealing and complex sealing, and just review some of the overall technologies that we've got. So I did want to add on a personal note, as I've told the story many times before, prior to me getting into sales of leak test equipment, or as I say, crossed over the dark side, I was an engineer at Cummins Engine Company in Columbus, Indiana. And one of the first things that I purchased or was involved with from a project perspective was leak test equipment. And we were new into leak test there in the fuel systems division, which I know seems a little crazy, but back in the mid 90s, we were just kind of stepping into that, figuring out what that was about, as opposed to just putting it on a functional tester and fluid blowing everywhere or leaking out. We started using leak test technology. So I got to know Gordon way back when, as this is 1995. So Gordon and I have been working together since 1995 on the customer side, as well as just working together. He's been a wonderful mentor to me personally, and he is a pro and awesome at what he does. So we're really excited to have him on to talk about custom leak test technology. So anything you want to add to that, Speedy?
Oh, thanks, Russ. All the gray hair that's come with that amount of time, I'm telling you.
Feel it with me, right? Oh, mercy.
It's gone quickly, though. It's crazy.
Yeah, absolutely. Amazing. Well, again, thanks so much for hopping on. And as many of you know, we talk about it all the time, but Cincinnati Test Systems is the largest leak test company in the world. We're proud to represent them in Virginia, North Carolina, and South Carolina. CTS has grown, of course, exponentially since those early days in 1995 for us, right?
Yeah. Wow, the 90s.
Yeah, right.
Yeah.
Take that mullet back. Yes, go ahead and talk through this. Talk through this slide.
Yeah, so with CTS, we support all industries, heavily in automotive, and especially with the electric vehicle startups right now, and all that goes with batteries and water leaking into electrical components. So that's big in the industry right now, along with consumer electronics. IP67 requirements. We talk to a lot of customers about converting from this attribute test of no water leak at 1 meter of water over 30 minutes down to non-water leak rates. Yeah, there you go. That's where they started. And then getting into HVAC, all the new refrigerants that are coming out into industry. There's a huge amount of change happening. And as we're all at home, we're using our air conditioners more, our refrigerators more. And that is a big draw for leak testing as well. And then all the other, and medical's been really necessary this year specifically with everything that's going on.
Yeah, it's probably exploded, I assume, with all the respirators that are now being manufactured. Those all get leak tested, right?
Yeah, absolutely. We worked with one of our main automotive customers to help them convert one of their assembly locations to testing those types of components. And it was a big project for everyone when they did that.
Wow. Yeah, and the speed of light, right? It has to happen yesterday.
Yep, it happened over a weekend.
Wow, that's amazing. And then something I think what not to get too deep in this, but it's amazing what we can do when we put our mind to it, right? It's when we align all the resources and we get behind something. we can just make it happen here in the U.S.
Yeah.
It's
Yeah.
pretty awesome.
And then,
Oh,
well, no, you're good.
okay.
All the other industries that we support, everything is leak tested with technology. The technologies we support are all of the ones that have measurable testing techniques: pressure decay, vacuum decay, leak and blockage. I'm not just measuring pressure change associated with a leak rate, but also making sure the part's not blocked using pressure technologies. And then mass flow testing, which is similar to pressure decay, however, a little different. And then testing for actual flow through products or as a leak based on flow technology. And then tracer gas testing using helium, hydrogen, other gases like argon, CO2 to test using sniff techniques, purging containment techniques, accumulation of that gas in a confined chamber, and then hard vacuum mass spec testing, controlling background.
Been some tremendous advancements since we started in '95 in that tracer gas technology.
Oh, yes. Yeah,
Where
with some of our patented technology in nitrogen purge, that's really helping test at less cost down to lower leak rates, like 1 times 10 to minus 5 and minus 6 cc per second leak rates.
Yeah, for sure. Well, let's talk about, Gordon. We're going to talk about test system planning. What does the customer need to supply to a potential supplier so that they can get an accurate quote?
Yeah, so the biggest thing is understanding the requirements for that in a statement of work. It doesn't have to be a lengthy statement of work. Just identify what is the project, what are the details, and some written understanding of that component, the technical requirements, and then specifically test specifications, leak rate, test pressure. And if you don't know those things, there's some correlation associated with test pressure. What's the operating pressure of the part? Is it an IP67 spec? Well, that's easy. It's 1 meter of water. 1 meter of water equals 1.4 psi. And then leak rates, identifying either a pressure drop or the correlated flow, volumetric flow rate of that specification, 1 SCC per minute, maybe 10 SCC per minute.
What if a customer comes and we've heard this many times in our career is hey Russ, I need to build a leak tester so I can stop dunking these parts underwater. Um, and then of course we ask the question, well, what's the specification? Well, no bubbles.
Yeah.
So how do you help a customer through that process?
Yeah, so the fun thing about no bubbles in our industry, everything leaks. It's just how much you don't want it to leak. So since everything leaks, you may see bubbles that water will not leak through that same hole size. So identifying what that really means, what shouldn't leak into and out of the part. Is it water? Is it liquid? Is it oil? Or is it a compressed gas like freons? And that helps us help our customers dictate what they should use as a leak rate.
Yeah. So the question is, what are you trying to contain, right?
Right.
You either contain or keep out
Yeah.
is a part of that questioning process for sure. I used to always tell customers, especially in the machining world, people can wrap their mind around this, and they would say, "Well, Russ, it can't leak. No bubbles, it just can't leak." And I said, "Okay, well, I need you to make all of your parts 1 inch plus or minus nothing. Every single part has to be that, because that's equivalent to what you're asking for as it relates to the perfection associated with parts that don't leak, right?"
Yeah. Yeah. So there's some calculations you can do, but that gets you within 50% when you start comparing viscosities, and it tends to be dictated by your leak path. Hole size leak path will dictate leak rate of fluids. And
Yeah.
we can get into further details, but
Yeah, no, that's a good. I mean, I think it's good to just help people wrap their mind around to understand what are some of the different elements of determining what the appropriate test pressure and leak rate should be for your application.
Yeah,
So
absolutely.
what's next?
Oh yeah, so then you take leak rate and you understand what a production rate is, understand the customer's takt times and production rates, and then calculate estimated test cycle time, and then put that back into that calculation and say, okay, will we get throughput for this application or for this program with one station, or does it take 2 or 3 stations? And then budget allowing, does it require automation, or is it a manually loaded, unloaded operation? So budget's always necessary too, to understand as you dive into a project and what the throughput requirements will be.
Yeah, and I know you've experienced it. We experience it all the time where a customer gives you the forearm shiver as it relates to providing that budget information, but it's not so that we can match the budget to well, it is at some level, right? So if we would normally charge 50,000, the goal isn't to say, okay, well, this would cost 25, but we're going to quote 50. The reality is that if they say the budget's 50, and it's going to take 75,000 to do what you want to do, then we need to be able to have an intelligent conversation about either adjusting the budget or taking some of the expected machine content out. Correct?
Yeah. Yeah, and we're going to see some slides of machines with different
Yeah.
technical requirements. And yeah, knowing budget, knowing throughput, it can be a manual process that takes a little more time, or you have to automate to accommodate that throughput requirement. And obviously, there's costs associated with automation.
Yeah. So depending on the production rate, you might need a dual station,
Yes.
or even have 3 parallel stations, or any number of dynamics there. Well, let's talk about cycle time. That's
Yeah.
what's going
So
to determine all that.
yeah. So cycle time, especially in leak testing, we're working with physics. The physics side of it is the ideal gas law. And we use the ideal gas law derived down to what we call the leak rate formula. And we can identify time knowing the volume of a part, the volume of test line, and the volume of the pneumatic manifold of the test circuit. That volume times delta P, a pressure change that will be measured using pressure decay. We look for a 0.02 PSI as a conservative factor, times 60 seconds per minute. That quantity divided by leak rate, that's the volumetric flow of air from the part, times pressure, which is atmospheric pressure at sea level. That standardizes this whole formula to standard conditions. In this case, we've got an example that a 0.02 psi drop for a liter part equals 8 seconds. So with that, we can calculate a full cycle time, estimating same amount of stabilize as test time, fill time, 8 seconds. If it's a small part, we might cut that in half down to around 4.5 to 5 seconds. And then you've got some unclamp time for sealing the part, and also exhausting the part back to atmospheric pressure. So that allows us to estimate some total test cycle time. And loading and unloading is customer dependent. Is it manually loaded? And how close will that operator be? And how heavy is the part? So you can estimate some times around that.
I think some of the pushback that we get as I think back in the many times that we've gone through this calculation is that we want to be conservative, and the tendency is that a customer will want to match whatever the cycle time is for their overall takt time. They want to try to match the leak test into that takt time, and that's kind of the tail wagging the dog as it relates to achieving so we do this because we want to achieve a specific gauge R&R, right? The ideal gauge R&R.
Yeah, absolutely. That you don't want to overstate a quick cycle time and then come back and have to add multiple stations, because that's a economic factor that may not be budgeted for later in a project. And everyone's got to know the end goal and the end understanding when you start this.
Yeah. So tell me the reality, not the ideal, right?
Yeah.
Now let's go back. One of the things that I get, one of the questions that I've gotten all the time is, well, why 0.02 psi on the delta, Russ? Why does that matter?
Yeah, so 0.02 is a conservative factor. It's something that we found fits with absolute pressure decay testing. And we look for two factors, a 2-to-1 difference between a good part and a part that has a leak in it. And that 0.02 kind of fits that window as well. Lots of times as we use more sensitive technology that we'll talk about, differential pressure decay, you
Yeah.
can see a lower pressure drop, and that allows us to get a faster cycle time. However, this is a good starting point for lots of applications.
Yeah. The majority, right?
Yeah.
Okay. Well, let's talk about achieving a more accurate test based on the technology that we're applying.
Yeah. So we've got two graphs here. The one on the left is absolute pressure decay, and you see your upper slope is a known leak, a known leaking part tested multiple times. The lower slope is a non-leaking part tested multiple times. And the average, you see there's some separation after 25 seconds of test. And then comparing that to the right, a differential pressure decay, we can see a greater difference between those two slopes. And you see your non-leaking part has a lot more even slope in it. And the reason for that is there's some using differential pressure decay, we're pressurizing our part and we're pressurizing a reference volume and comparing a pressure drop of your known tested part to this known non-leaking reference volume. And there's some thermal events that are nulling themselves out
Hmm.
that you typically see as noise in the other sequence.
That
And
makes a lot of sense.
yeah, yeah, and because of that, we can see a difference between a known good part and a known good part more quickly, reducing the cycle time based on test time reduction.
So with the differential technology, as I look at this, I assume was the same part that we were
Yes.
thinking. So given the noise, it looks like our number is about 0.016 psi, maybe a little bit higher than that was the average loss. And then with the differential technology, given that same cycle time, was about 0.013.
Yeah.
Um,
Yeah. So there was a few, what is that? Thousandths of a PSI difference. So,
yeah, I always say that. Yeah, it's it's about as much air as a moth farts, but which is not very much, but still, it's an interesting eval. But that's such a stable, the differential pressure decay option. Now, let's talk about that reference volume. I think some people get the idea that the reference volume has to be exactly the same as the part that we're testing. Is that the case, or what type of variability is allowable, or what do we need to watch out for as it relates to that reference volume?
yeah, reference volume is a good thing and sometimes a bad thing. It really comes down to leak rate and size of part and test pressure. It's very easy to take a differential pressure decay system and cap off the reference side to get a very repeatable test. 90% of our customers test that way. As you get into some possibly lower leak rates, comparing some very precise measurements, then you might have a volume very representative of the part volume. Uh, the problem with having a reference volume is there's another part in the system now that could leak. There's another part in the system that could change temperature based on external effects. So that's something to keep in mind when you use specialty testing like this.
Now, does that affect when you add that volume? Is it going to negatively affect the cycle time because now you have to fill up both volumes? Is that a factor?
No, that's usually not a factor unless it's a really large volume. Well, I'll say yes, it could be based on size of the part, size of the reference volume. So there's no special answer that's one way or the other for that one. It's lots of these are application driven discussions and formulations for testing the part accurately.
So what are some ideal applications for differential pressure decay? Just to kind of give
Okay,
some
yeah,
perspective to the customer.
some really good ones. Higher pressures, higher than 50 psi. That way you've got this thermal event that nulls itself out. Really low leak rates, small parts with low leak rates. Differential can test very well on those. Those are a couple of the really good ones to look at.
So when, as Gordon's talking about thermal events, one of the things to keep in mind is that, or as it relates to higher pressure, we've got to remember that when we are pressurizing a part, there's essentially no pressure or technically 14.7 psi pressure in the part. If we're going to put 100 psi in the part, what happens is the air that we're putting in is compressed, and it is going to expand as it goes into the part, and then it's going to compress again. And that thermal expansion, we don't that expansion and contraction of the air, those molecules are rubbing together. They're getting energy from each other, and it creates heat. Now, obviously, we don't see that. We can't. We can only see it in the, as you can see, these graphs right here on the absolute pressure decay graph show that thermal event that we're seeing from, and a great bit of it is due to the expansion and then eventual reduction in the air that's being put in there because of the pressure that we're having. So is that a correct assessment?
Yeah, that's a really good description. An example of this, I had to haul some rocks in my truck this weekend. So I pumped the tires up to 70 psi using a hand pump, and immediately you can feel the heat in your hand pump line going to the tire just from that going from 60 psi to 70 psi. So that's the type of thermal event we're talking about with compressed gas.
Yeah, that's another good example. So here's a differential pressure decay circuit. Makes more sense here.
Yeah, so a DP circuit uses a source air. You pressurize your test part in this referenced capped volume through these open valves. The valve in here that's closed is V1 exhaust. That's closed to exhaust as the whole system fills up with pressure. You use an absolute transducer to measure test pressure going into the system, and then isolate all the valves and exhaust your exhaust valve. That way you actually isolate the whole system from air leaking from your source through your fill valve, and then compare a pressure change in your known good, or in your test part compared to your known good reference volume capped using a differential transducer. That transducer's ranged in the typically 2 or 5 psi range. So if you're testing at 100 psi, your fill pressure transducer is going to be a 200 psi transducer, and you've now reduced the amount of, you've increased the amount of resolution going into A to D converter for that DP transducer at 5 psi.
Yeah, so going into so for those of you that don't know or are unfamiliar with A to D, which I'm sure we have a bunch of nerdy engineers like us on there, but it's analog to digital converter because all of these these signals from the transducer needs to be converted into something that makes sense other than electricity, right?
Yeah. Yeah, so it gives you, in simple terms, gives you a very, very fine measurement compared to using an absolute transducer.
Yeah. Excellent. Let's talk about some of these industrial applications.
Yeah, so these are 3 of the CTS instruments that support DP technology. Our latest MH instrument, it's a headless unit. It interfaces and is set up through a PC interface. The really nice thing about that instrument and the PC interface, you can actually see pressure curves very easily and start your test, stop your test through the PC. once everything's set up, then interface it with a PLC or simple input if you want to keep it that simple. And it will test parts all day long, giving red lights, green lights, and ranges from vacuum to 200 PSI. The LPC 528 is a benchtop version of that with an operator interface, and gives you all the same capabilities uh, along with a manual or electronic regulator in a benchtop design. And then our I-28 is our instrument we use on lots of turnkey test systems. It has five tooling control motions with feedback. It has other 12 inputs, 12 outputs for other controls with, and it also has Ethernet IP interface for Allen Bradley PLCs that we've
So,
written. Go
oh,
ahead.
okay. I was going to say, if so effectively, if you've got a casting that is machined or not machined, or you can just you can build a machine utilizing the I-28 to control all the seals as well as the test, accept, reject, all that. You put the part on, you hit the opto buttons, comes in, seals in the part, and all of that is controlled by the I-28.
Yep, absolutely. And it's got perfect ranges, vacuum all the way up to 500 psi. So it gives you a full capability of selecting the right instrument for the right range instrument for the application. It can do DP, it can do flow, or just standard pressure decay also. So there's a lot of capability in that instrument.
Yeah, for sure. Definitely a workhorse in the industry.
Yep.
Let's talk about this is always a hot topic, and we should probably have a separate session just talking about runoffs. But let's help people wrap their mind around, because I know from my experience when I was at Cummins, when we had a gauge R&R for the manual gauges that we would use, our expectation was it'd be 10% or less. And then when I got into the leak test industry, because of all the dynamics that go into it, between 30 and 20, and or at least less than 30, and then less than 20, obviously depending on the application. So let's talk through where that has come from since mid 90s when we were first exposed to it.
Oh, sure. Yeah. So this is a gauge R study. And it's 4 parts. A full gauge R&R study would be 10 parts, 10 times each, 3 operators, and in this case, what we're doing is testing this part over and over and over to see what kind of a variation you see test to test, and then comparing it against 4 other parts test to test. And it gives you a good understanding of how well your test cycle time set up and how well your instrument is measuring a pressure change converted to a leak rate test to test to test. And it can, as your percentage goes up or down, goes up, means you've got some variation associated with either your instrumentation or your test cycle time. And then comparing that, conducting the testing, you can reduce cycle time if you've got a really low R&R study, putting a little more variation into the system so that you don't go past what your set value may be. And like you said, Russ, 10%, 10% gets really challenging with pressure decay testing because of all the exterior variation that comes into air leak testing, temperature changes, part porosity, ambient temperature associated with it, how the part's loaded, an operator's temperature, body temperature will affect part temperature.
Part volume variability.
Yes, castings will have some variability, and to get below 10%, you'd have to have way less than 10% variation part to part.
In some cases, I think it's tough for people to envision the sensitivity of the instrumentation, and why these things should have such an impact. But oftentimes with customers, what I will do is just touch the part with my hand. So I'll press hold while it is in test. And if you touch the part with your hand or even just get it close, that thermal exchange is almost immediately noticeable in the gauge reading on the instrumentation. And
Yeah.
when we do that, the customer's eyes are wide open. They're like, whoa, they are blown away by the sensitivity. And that kind of gives them some perspective as far as what they're dealing with and how challenging it can be to achieve that, 10% gauge R&R that, their quality engineer says that they must achieve. But in the reality of the dynamics associated with the test, it's not achievable.
Mm-hmm. Yeah. We have some customers that pay operators for production throughput, and operators learn real quickly that if they put their hand on a part that is failing, they can actually cause it to pass. Something to watch out for.
Yeah, for sure. All right, excellent. So here's a gauge R&R study, some more.
Yeah. So this is a full-blown gauge R&R study. Not only is it 10 parts, 3 operators tested 10 times each, it also takes into account test variation and then equipment variation, and also appraiser variation, total R&R, part variation, and then the total variation in the whole system.
And so the appraiser variation is the operator, right? Just to
Yes.
make sure that's
So
clear. Okay.
so that as you change operators, you will see variation associated with each of the different operators. Like I said, how they load the part, body temperature, um, all of those types of things affect air leak testing. What we look for when we run a machine off is equipment variation specifically.
Mm-hmm.
Um, Customers obviously are really interested in total variation. However, those are things that they will need to look at how they control in their testing environment once they have a machine on their floor.
Sure. Very interesting. Always a topic of discussion. Again, we could talk through many examples to show each of those variations. But it's amazing, and what's pretty cool is that we can separate out equipment versus operator versus part with the this format.
Yeah, yeah, absolutely.
So let's talk about some sealing applications.
Yeah, sure thing. So, see, in leak test, everything leaks, and if you can't measure a non-leaking part because your seals leak, then you've got to figure out the best way to seal your parts. And we we have tons of experience uh, sealing parts using different things like CTS connects. You see the blue seal in this picture, flat seals, parts loaded on bases on a tooling plate that moves into a tooling station. What that does is allows a lot of
Oops.
operator load area and really short stroke cylinders so that the part can move in under the seals and you don't have as long a time to wait as those seals advance to the part.
Yeah, what people don't see is a big uh, filler block that this part actually goes over.
Right.
And depending on, you can also run, different parts on the same machine by having a quick change filler block and maybe changing some of the strokes or of these seals and readjusting them as well, right?
Yep, absolutely. And you with this, you'll see. You can go on to the next
Okay.
slide. That's
Okay.
great. So with this, you can see different types of test systems. The one on the far left is a very simple, manually loaded, manually operated tooling down to the part. We use a pneumatically actuated CTS Connect that's controlled by the I-28 instrument. So it positively holds the part during test, so the part's not moving or unsealed. And then at the end of test, it exhausts the part and then exhausts the seal so that you can manually unclamp it. Uh, That's one of those budget related, cycle time related, let's keep the cost as low as possible and simple as for an operator to utilize.
Sure.
And
And
then
get a little more complicated here.
Yep. Yeah. So that's like the first one we saw. It's a part loaded on a automated slide to move the part in underneath tooling, and then CTS connects that are pneumatically actuated to seal certain ports, ID and OD ports.
And this
Um,
dual station example here.
Yep, in a dual station, the red drawer is actually a automated or a locking drawer. So when a rejected part is measured, the operator has to unload that part, put it in that drawer, and then close the drawer to verify that that rejected part doesn't get down the production line. And some of the things you don't see in that one compared to the center station. The center station's got a barcode scanner on it, manually used. So you manually scan your part and connect that serial number with your test data. The one on the right, that one has some automated barcode scanning in it. So it takes the operator completely out of the requirement, out of the sequence.
Yeah.
And oh, the test stands we just talked about were pressure decay and mass flow applications. We also supply instrumentation for tracer gas testing. Our TracerMate 2 instrument conducts manual sniffing on a cart, and it can also do automated purge clamshell testing. And then the center test stand is an automated, semi-automated machine that's doing helium accumulation. That's a part tested within the orange chamber, and helium being tested for its concentration rate of rise in that chamber. It's also tested in a background of our atmosphere, which is 5 parts per million helium. 5 parts per million helium equates to a 1 times 10 to the minus 5 cc per second leak rate. And if you
Wow.
ever need to, yeah, it's really low. Um, and if many of our customers test lower than that, and they need to use helium hard vacuum mass spec testing, which is evacuating all the gas around the part in the chamber, and then measuring helium leaking into this vacuum source with a mass spectrometer.
Yeah. So, and for those of you that say, why would you use a tracer gas? Some of the main reasons that we would use or apply tracer gas to an application is that maybe it's very high pressure with a low leak rate, or it could be low pressure with a low leak rate. But it's really the leak rate has a big determining factor in that. And then the beautiful part of tracer gas is that thermal events that occur, like the say thermal events, not like an explosion, but the impact of thermal change on the test is not even a concern as opposed to mass flow pressure decay technologies.
Yeah. Yeah, so testing all the variation that we see in test, it's choosing the right technology to reduce as much variation based on the leak rate that you need to test for.
And it's that balance between cycle time, accuracy, and cost, right? It's
Yeah.
the dynamics and the balance associated with that.
Yeah.
So, well, I think so. We've come to it's 12:07. So I always always promise to keep it to a half an hour. Is there anything else that that we should hit along the way, Gordon, or is this a good place to wrap up for everyone?
Yeah, I think this is a good wrap up and a good starting point for customers that need to dive into this deeper.
Absolutely. Yeah. I mean, I can't thank you enough for taking the time to hop on this call with us. Certainly appreciate you. Always appreciate you as far as your knowledge. You've been around 25 years. Is that right?
Oh yeah, 25 years in leak test and what 30 some years in manufacturing of equipment. So it's half a lifetime.
That is, yeah, that's a lot of experience. So I've always, again, just appreciate you and appreciate all your help over the years and the mentorship and everything that you've done. And we always want to thank our customers as well. Thank you so much. We do not exist without you. It doesn't happen unless you buy equipment. So our mission at CapEx Sales is to always be adding value. So we want to make sure that we're doing more of these, having more of these conversations. We welcome feedback from you as far as what else you would like for us to talk about. We're going to have Gordon back on, and we're going to talk about troubleshooting and how to troubleshoot leak test equipment. We'll talk about sealing techniques. We'll just, talk about anything that you are curious about or want to understand more. We'll be sharing that with you. So again, Gordon, thank you so much for taking the time today, and have an awesome rest of the day.
Hey, thank you. Appreciate it, Russ.
All right. Take care. See you, everybody.